My name is Maggie Swift, and today I'll be giving an overview of the first 6 months of my postdoctoral project, which uses computer modeling to answer policymakers' questions about wildlife movements. And today I'll be using elephants as kind of a proxy for wildlife movements in general. As a quick note before we get started, whenever you see this picture of a real elephant, I'll be talking about real GPS data. And when I'm talking about simulations, you'll see this picture of a simulated elephant. Across the globe, and especially in southern African savannas, wildlife rely on the free movement across heterogeneous landscapes to access resources, which facilitates biodiversity and population resilience to disturbance. But human infrastructure and activity often inhibit these crucial movements. In particular, the management of livestock disease has often relied on these veterinary fences separating wildlife and livestock, which can have unintended consequences for wildlife. Today, I'll specifically cover the consequences for a savanna elephant in the Kavango-Zambezi Transfrontier Conservation Area, also known as KAZA, so thanks to Ryan for already introducing this region. The largest terrestrial transfrontier conservation area in Africa and the world. It was created in 2011, an international agreement between 5 southern African countries to facilitate the free movement of animals across international boundaries. However, major linear barriers still limit wildlife movement within KAZA. For example, in this region, highlighted here at the border of Namibia and Botswana, animals naturally move around the region to access seasonally available water and vegetation near the Okavango Delta, but veterinary fences have restricted their movements. Here I'm going to be showing some data from real GPS data from female elephants, here as a proxy for elephants traveling in herds, because these females are traveling with their young and with other female elephants, collared in Botswana in gray and Namibia in red. As you can see, the red and gray aren't mixing very much, right? So these fences are really separating these populations in the west, and then in the east they're able to mix because there's less fencing in the way. This lack of crossings by female elephants is probably due to the fact that even if an elephant, the male elephants can push right through the fences, but there's these steel cables that remain in the way for a young elephant that can't cross over, and the mothers won't leave them. Some of the general consequences of fencing for wildlife include a disruption of natural migrations, reduced resilience to drought, deaths from entanglement, which doesn't really affect elephant, but a lot of other wildlife can get entangled in these fences and die, increased population density, and increased human-wildlife conflict. And these last two are really important for elephant. As Ryan was talking about, population growth rates usually about like 4% and even less in this region, but actually in where I'm pointing out with this green arrow, it's over 5%. This is like a box of elephants, a lot of human-elephant conflict going on here. But through some work with Cornell's AHEAD group and regional partners like SADC, non-fence-based foot and mouth disease management approaches are now possible and accepted in the region. And foot and mouth disease management has been one of the main drivers of fencing. So this is really important time for conservation that now we don't have to rely on these fences for disease management. So targeted fence decommissioning can lead to relief of high-density population pressures, like in the area I just talked about, improving wildlife population resilience, increasing sustainable tourism options, and reducing human-elephant conflict. But if you're a manager or a policymaker, you might be hesitant to adopt a new management tool without knowing its actual effects on the landscape. So that's where my project comes in. The goal of my postdoc is to provide computational tools to help policymakers answer questions like this one: how will elephant movements change if key fences are decommissioned? So in a nutshell, my project is taking real GPS data, plugging it into an agent-based simulation, and then trying to reliably predict savanna elephant movements under future changes, and specifically fencing in the region. But because I'm only 6 months into a 2-year postdoc, I'll focus this presentation on the simulation itself and its modeling inputs rather than validation techniques and final results. You can check with me. Maybe next year I'll present some of those. But first, I wanted to introduce the concept of an agent-based simulation. An agent, in this case, is just an individual elephant. We define a list of probabilistic rules for the individual's movements across the landscape based on real GPS data and landscape-level data. And then the model randomly chooses movement parameters within those rules that the simulated elephant will exhibit. These rules can be based on many features, but in particular, I'm going to be focusing first on responses to environmental features, activity states, and responses to barriers on the landscape, so those fences I mentioned before, and also roads. First, environmental responses. The following environmental relationships I'm going to present are already well established in this ecosystem, but I think it's important to quantify these relationships so that we can put them into the model correctly. So first, we know that elephants travel significantly further in the wet season than in the dry season. This is because an increase of rainfall brings with it an increase in available vegetation on the landscape. Here, I have 3 years of rainfall data shown. In blue is spikes of rainfall. You can see clearly the wet season versus the dry season where there's no rainfall. And then below here, I have the hourly distance traveled for these elephants, which I'm going to term step size during this presentation. And step size does not mean like the physical size of a step for the elephants. It's the distance in between hourly pings from a GPS recorder. So you can see that these step sizes really increase during the wet season. And we can quantify this using a linear mixed effects model with hourly distance traveled by season and then random effect of animal ID. And we have an increase of 115 meters during the wet season as opposed to the dry. We can do a kind of a similar analysis, but thinking about access to water. So elephants during the dry season really cluster around these water sources because they need to drink daily. But during the wet season, they can kind of spread out over the landscape. So this is GPS data from one female elephant over 4 years. And you can see that she travels way further from the Okavango River during the wet season. But I will also point out, you see the fences are still restricting her movements. So again, we can look at a simple linear mixed effects model, looking at the distance from river as a function of season. We actually have an increase of 6,000 meters, or about 6 kilometers. Finally, we used a habitat selection model to investigate how elephant herds use different spatially distributed resources. In this case, is canopy cover class. So this is the KAZA region. In blue, you have more open landscapes, and then green is more closed landscapes. So very briefly, the way that this works is you have some kind of a landscape. Let's see, you can imagine this is one of those points on the map, and we take real data from a real elephant. We give it a bunch of available places that it could have walked to, and compare those to the ones that it actually did walk to. And if you compare those two sets of points, you can get a proportion in each cover class used versus available. In this case, it's going to be used as in black and available is in gray. The thing to note here is that in open landscapes, this middle bar, the proportion of used open landscape is greater than the proportion of available open landscape, meaning that these elephants are kind of choosing these over what you would expect from just random selection. We can also put this inside a generalized linear model with use as a response to cover class. And this is, I don't want to explain the full figure, but what I want you to notice is that the darker pink means that you're switching from one of the other cover classes to the cover class in the row. So in this case, elephants are choosing to move from closed or sparse landscapes into open landscapes. Okay, so next up we have activity states. So this is just the idea that elephants, when they're moving around the landscape, they're not just random particles, right? They are doing things while they are moving. And so we're going to use a hidden Markov model to decompose elephant movement into exploring, resting, and foraging states, which Gareth had mentioned in his talk on Tuesday, so thanks for priming the audience there. As an example, I'm showing you female elephant data from one elephant in 2015, and she's in Kruger National Park in Namibia. So first, you might have a resting state. I'm realizing it's a little bit hard to see, but when an elephant is resting, you might expect them not to walk around the landscape too much. So taking short steps and having an even distribution of when they're choosing to turn from their last point. For any HMM nerds out there, I'm going to put up some of these graphs of frequency distributions of step lengths and turning angles, but you all don't have to worry about that too much. Next, you might have an elephant that's foraging. You might expect them to take a little bit longer steps and maybe turn around and take a little bit of a different approach to the landscape. And then finally, an elephant might be exploring or having a concerted walk towards a destination. And so with this female elephant, we can decompose her movement into these three pieces. And what I want you to notice is, maybe I can do this laser pointer, these central points where the elephant is moving out and then foraging around the landscape and moving back in, which is really cool, especially if you know anything about elephants. They love water. So these are actually water holes that they are moving out from and moving back in. All right, and the important thing with the activity monitoring is that, or modeling, is that you can take this and put it with the environmental pieces that I was showing before. For example, wet season release from river dependence. The wet season expansion pattern actually only seems to apply for foraging and resting states and does not apply for the exploring state. And this makes sense when you think about, well, these elephants are exploring to get water, so it makes sense that they're needing to drink still in the wet and the dry season. They're just foraging and resting further from water sources. Finally, we have to include individual responses to these different barriers on the landscape. There's a 2022 paper with Robin Naidu, who's one of my co-advisors, studying elephants in Botswana and Namibia. They found that linear features are differentially permeable to elephant crossing by feature type and by elephant sex. So here, what I want you to notice is that the bars for river and road crossings are higher than fence crossings, right? So it's easier to cross a road than a fence. And then also that the females in black bars are always lower than the males in gray bars. And again, this is because they're in larger groups. They might have young with them, and there's actually no bar for fence crossings, so the females are never crossing the fences. And here's an example of one of the females just in January of 2021. You can see she comes up across the fence and bounces off and goes along her way, but she's not able to, or chooses not to, cross the fence. And so once I had all three of these pieces together, I wanted to start modeling these and simulating these movements, but then I realized is that an agent-based modeling framework that did everything I wanted it to didn't really exist. So I had to kind of work on my own. So building on this great R package by Marshall and Duthie from 2022, I was able to add on to their work and add linear barriers onto the landscape and augment their code to take in actual environmental raster data instead of just matrices. For any wildlife veterinarians in the audience, you've probably done a postmortem of an elephant, but this is what a postmortem of an elephant for me looks like. This is a lot of the code that I've written for this project. And I don't put it up here just to show how much I've done, but also to say that elephants, again, are not just random particles on a landscape. So it takes a lot to make your simulation match elephant movements. So thank you. So in my remaining time, I'm going to go over how this model works. Sorry about that. So you start with some current position on the landscape. You choose an elephant's, randomly choose an elephant's activity state that might be in, resting, foraging, or exploring. And then you choose a landscape to match that. So when an elephant is foraging, they might be looking for different things on the landscape than when they're exploring. Then we choose, again, those random points on the landscape and add in all of our fencing data. And for some of these elephants that might, let's say this fence is permeable, the elephants might be able to cross some of the time. We're gonna take that permeability and turn it into a probability of throwing out some of these points. So we throw out one of the points and redraw, and then have the elephant actually select a point on the landscape. So what this looks like for agent-based simulations, at first, hopefully you can see this elephant that starts out way down there. It just ignored the fences, and it took me a long time to get them to actually recognize the fences, but then I have some elephants wandering around the landscape and bouncing off the fences, and that was great. I was able to also add in some of these waterhole relationships that we saw before. So this is an ongoing process. I've just been doing this for 6 months, so again, I'm really excited to show more of this next year. And returning to a workflow from before, next steps is validation with real telemetry data. And I wanted to add in some other components I know you guys are going to ask me about, which would be density dependence, migration, and even some things that were mentioned in previous talks, like the species and memory and adaptive perceptions on the landscape. Finally, with my remaining time, just like stepping back for a sec, as the southern African landscape warms and dries over the coming decades, like pictures like this are going to be more and more frequent in news media, and thinking about these elephants on the landscape. Not suggesting that Hwangi's elephant death problem is related to fences because it's unfenced, but like these kind of stories are just going to become more and more apparent on the landscape. So addressing this fencing issue when elephants need to move to access resources, especially during drought, is going to be more and more important. So with that, I'd like to thank everyone here and my funders and co-authors.